All right. So part two, chapter 5, part 2, I should say. So we were talking about inference for numerical data. It is really important, so I'm going to emphasize it again, that this is for numerical data, although I didn't write that very nicely. Now that I'm highlighting it, I can see that I didn't write it very nicely. But now today, what we're going to talk about is what if we have two samples of data that we have collected? So two samples of numerical data, and we want to compare those two samples, right? And so today we will consider two samples of numerical data. That we want to compare the means, or maybe I should make that make sense. And we want to compare, you know what? Just leave it. Today we will consider two samples of numerical data. There are two different ways that we can have two samples. So when you're thinking about two samples of data, I want you to imagine two columns in your spreadsheet, right? One column of data would be just one sample, but now you have two columns of data. And there are two ways that that this data can behave. So the first way that we're going to talk about is we can have paired data, right? So paired data is when we have two observations on a single subject, typically. There are a couple of others that I want to talk about as well, but typically paired data is two observations on one subject. So now I want you to just imagine, what does that look like in terms of your data set? Well, it's going to look like this, right? So here you have your observation number 1, number 2, number 3, number 4, or sorry, I should call this subject because it would work, but subject number 1, so person number 1, number 2, number 3, number 4, rat number 1, rat number 2, etc. Or kind of a little bit nicer to think about. Plot number 1 for my tomato plants, plot number 2 with maybe different soil for my tomato plants. It works for a lot of different scenarios. And then here we have observation 1. Maybe here I'll say obs 1 and obs 2. Maybe it's a pre-post. So a pre-score and a post-score is really common for paired data. So then we want to look at the change over time, right? So observation 1 is maybe when you were admitted into the study, and then observation number 2 is after you've completed some sort of training or whatever at the end of the study. That would be paired data. So here, right, you've got maybe some number, because it is all numerical data, right? And so here, we have two samples that are paired. Right, so that's the first section I want to talk about. But just so you know where we're headed, the other way that we could have collected two samples is, of course, well, what if if this sample and this sample had nothing to do with each other, right? So we didn't have the same subject here. We just had sample 1 and sample 2. So that's the other way that we could have two samples, and we would just want to compare the means of those samples. Is the mean of this one higher than this one, for example? So let me write that down here. So the other way that we could have it is independent samples. Okay. And so that's when there's no natural pairing between the two samples. So for example, maybe we have our data set here, and it looks maybe like, sure, UBCO versus UBC Vancouver. Maybe we're looking at, let's get weird, maybe the heights of people, right? Height is a numerical measurement. And so of course, then we would be analyzing the mean height at UBC Vancouver versus the mean height at UBC. Oh, I really don't think that we would find a difference. Who knows? GPAs, maybe, I don't know. Whatever numerical measurement you want to compare across the two campuses. Notice that you have UBCO and you have UBC Vancouver data, and there's no natural pairing there, right? And that's okay. We just have to treat it like they're two independent samples. So either way, it's going to dictate, so how your two samples are laid out is going to dictate how you analyze it properly, right? And that's all we're doing here. So there's no right or wrong. It's just we have two different ways of analyzing these two samples and comparing these two samples. So here, let's say we've got UBCO and UBC, UBC Vancouver, and here's some number, here's some number, here's some number, and here's some number. What we'll find later is they can even be different sample sizes. How cool is that? And we can still handle it. So here, now we have two independent samples. So it is your job, our job, to be able to determine, so read a question and determine, are these data paired or are these two independent samples? So we'll go through, we'll start with paired data, and then we'll introduce independent samples and how do we deal with those. But I also want to point you towards the formula sheet here. So 5.2, sometimes I call it matched pairs, paired data. What we're going to be analyzing is the mean difference, and we'll talk more about that, obviously. But here is the layout for what we're going to do. If you look closely, it should look kind of familiar from earlier in chapter 5, right? Just all these diffs everywhere, spoiler alert. But then also while we're here, right, we can talk about two sample means, or I like to emphasize it by saying two independent sample means. Okay. So let's start here. Okay. So paired data, let's see if I can get this whole, sure, great. And you know what? I'm just going to grab this while I'm here. Okay. So we're starting with paired data or matched pairs. I like to say matched pairs sometimes because it really emphasizes that you've got these pairings across the rows. And so let's just skip over to the sidebar here where it emphasizes. So if we've made two observations on the same individual, Or if we've made one observation on each of two similar individuals, so you could treat siblings typically as a pair, that kind of thing, especially if you're dealing with twins. Cha-ching for research, right? Um, no, they're individuals, but we can typically, depending on what we're talking about, we can treat them as paired data, and then we can extract information from that, because there's real value in being able to say that, okay, I can assume that this individual or these observations come from basically the same person or subject. So pre-post data is really common, right? Before and after. Things like test 1 and test 2. Oh, scary. I can do a hypothesis test to see if we have improved significantly from test 1 to test 2. Oh, what? You can do that? You can. And I do. But that doesn't matter. I know, scary, right? So when we've collected two samples of numerical data that's paired, we use the mean and the standard deviation of the sample differences to infer something about the population mean difference. So what does that mean? When I know, mean. What we do when we have paired data, right, which looks like this, right? So I have subject 1 has observation 1, so maybe test 1 and then test 2. What do I do? Well, in order to capture that this is all about this or information from the same person, it's easier to talk about people. So, but it could be, you know, plants or rats or whatever. Or I don't know, stocks, I don't know. Trying to cover all my bases. Right, and so to try to capture that activity in, is there a difference from subject 1? Then what I do is I make a new column, and each column is considered a sample, right? So I make a new column of the differences. So I calculate each of the differences as I move across here. So observation 1 minus observation 2, for example. So I think it's a pretty sneaky trick. It's pretty cool that it works. But to compare the responses from the two treatments, so the samples in a matched pairs design, we find the differences in the responses within each pair and then record the differences in a new column, right? So that's what we were just saying. So what's important, right, is that maybe let's take a subject that I was really not strong in, biology. So my test 1 score was, I can't remember, but probably pretty low. And then my test 2 score was also pretty low. But that's because I wasn't very good at biology, right? And so even if there was improvement, right, as a researcher, I would want to see if there was improvement for me, right? Even though I myself, and now I'm playing two roles in this scenario. I'm a researcher and a student. Anyways, so I, as a student, am weak in biology. So test 1 might have been low. Test 2 might have been higher, right? And so we don't want to lose that variability within each individual, right? We want to retain that, okay, well, Emily, when the differences in her tests, there was improvement for her individually. And that's what we do when we take those differences, right? Because let's say you're really strong in biology and you get your test 1 back and you're so excited, you got a high grade, and then test 2, you got an even higher grade. That's great, right? And so then we calculate those differences, and then what we do is we analyze our differences as one sample. So now we're analyzing one sample of differences. One sample, well, that brings us back to part 1 of chapter 5, right? So now we're only talking about one sample and the mean of that sample. But the mean is the mean of the differences, right? Or the mean difference. And terminology can get a little bit boggy here, right? Because sometimes we'll talk about the differences in the means, which is for 2 independent samples. And then right now we're talking about the mean of the differences, or usually we just say the mean difference. Okay, and so it's kind of a special case of one sample means with sigma unknown, of course. So like I said, since there's going to be variability among the subjects, the change in each subject will be captured by the difference observed in each subject, right? And so taking my test 1 grade minus test 2 and recording the differences there, and then we analyze the differences, which means we can just kind of ignore the original data because everything that we need is captured in those differences that we've calculated. One thing that we need to remember is that it's really important that you're always subtracting in a consistent order so that a negative number always means the same thing, and alternatively, a positive number also always means the same thing in that scenario. However, the order doesn't matter, right? You just have to be consistent. Okay. So using a consistent order, but order, or I should say, but the order itself does not matter. If you think about a test 1 grade versus a test 2 grade, if you're doing test 1 minus test 2, what would be an improvement, right? Then test 2 would be larger than test 1. So then test 1 minus test 2 would give me a negative number. So a negative number would mean an improvement, right? And so that's why you have to be consistent because you don't want to switch it up halfway through, right? Sometimes you'll want to do something sneaky like, well, an improvement is typically positive, right? And so then you might want to do test 2 minus test 1 consistently. And then a positive number would be an improvement, and a negative number would be disprovement. No, I don't know. The word's not coming. And I'm moving on, so whatever. Now I'm trying to think of it. A decrease, no. It's not coming. So what's neat is that once you've reduced it to one sample, right, then you apply the one sample t procedures to the sample of differences. So that is if the assumptions for applying the t distribution are met, things like is each observation, so is each individual in your sample, are they independent of each other, right? And what else? Do the differences follow a normal distribution? And do you have a large enough sample, right? If it follows a normal distribution, then you're okay with a small sample size. So then we can use the one sample t procedures to perform inference about the mean difference, which I denote with a mu subscript d, or sometimes I'll even do or mu subscript diff, just to emphasize that it's the mean of the differences, right? All right, let me just grab some more notes here. Okay, so hypothesis testing for paired data is basically the exact same as for one sample mean with sigma unknown, which we just covered earlier in chapter 5, right? What's nice is once you've identified that you have paired data or kind of a matched pairs type of problem, then unlike for one sample mean where you have to figure out what number you're comparing the mean to, for paired data, it's actually predetermined. This will always be your null and alternative hypothesis, with the exception of potentially a different sign here in the alternative hypothesis, but that is kind of understood now. But besides that, you're always going to be comparing the mean of the differences, mu d, to 0, right? Why is that? Well, a difference of 0 would mean that I like the test 1, test 2 example, so I'm going to go back to that. If test 1 and test 2, you got the same percentage, well then, of course, the difference of those would be 0, right? So if we want to know if there's a significant difference overall, well then we would be comparing the mean of the differences to 0, right? And so when you calculate the differences, you'll also be able to find the mean of those differences, right? And that's going to be your sample mean of the differences. And you'll also be able to calculate the standard deviation of those differences. And that would be the sample standard deviation of those differences. And so here, right, what's nice is this. Oh, maybe I should specify that it does not necessarily include the sign there. This will always be the H0 and HA for paired data. Right, so that's kind of nice. That's a lot of work that's already done for you, right? And so with the exception of the sign, and the sign can be a little bit tricky. We already kind of touched on that, right? With test 1 minus test 2, well, if test 2 was higher, you would end up with a negative number. So then if you wanted to know if there's an increase, you would say, is the mean difference less than 0 in that case? Whereas if you calculated test 2 minus test 1, then an increase would be positive. So then your alternative would be mu d is greater than 0. So it depends on how you calculated the difference. And it can be kind of hard to wrap your head around in the beginning. But with a little bit of practice, you'll see, you'll start to pick up on it. Okay. So the only difference between paired data, because we're analyzing one sample of differences versus just one sample of data, and we want to compare the mean to some number, is that now we're comparing it to 0 instead. That is the number that we're comparing to. So when we do the test here, what's nice is that, okay, remember, we always do the test assuming the null hypothesis is true, right? And so here, from here, right, if the null hypothesis is always that mu d equals 0, we don't even really need to show that, right? So because the null hypothesis is that the mean difference is 0 for paired data, we're just going to jump right ahead and say, well, x bar of the differences, so the sample mean of the differences, minus 0. Well, I don't need to write that minus 0, but if it helps you, then go ahead and write the minus 0. But I also included the formula sheet down here. Okay, so I do have minus 0 here, but that's really just to emphasize that I've got a 0 here. Okay, so and that's always going to be the case for paired data. I guess on the formula sheet, I've got the full diff on here, making it look a little bit nasty, but at least it emphasizes that it's for the differences, at least. So then what we're going to be doing is we're going to find the sample mean of the differences, right? So here, this is the sample mean of the differences which is really just taking all your differences, your column of differences, and finding the mean of those values, right? And then here, the standard deviation of the differences. So this is the sample standard deviation of the differences. Now, you don't want to be calculating the standard deviations by hand for data sets larger than like 5. You can, but it's a lot of work, right? And so I would recommend that if you ever need to find the standard deviation of the differences, then you could go to Excel. Excel can definitely help you with that if you're comfortable with using Excel. Or there's lots of free online calculators. Just Google standard deviation calculator. It'll ask you to enter all your data points, and then it'll just calculate the standard deviation for you. So we should be using software for this stuff now. But I make you calculate the standard deviation at the beginning of the course just so you appreciate all the work that software is doing for you, and also to see what it is. And then, of course, the n of the differences. Let's see if I can find a non-pink color. Purple. So here, this is the sample size. ND is the sample size of the differences, right? Which leads us to our degrees of freedom, right? Because I'm calculating a t. Because I'm using a sample standard deviation, I'm calculating a t, which means I can use the t table to find the p-value. Are you keeping up or what? Oh, t's, p's, q's, no. Well, later. So because I'm calculating a t, I need to know my degrees of freedom, but the degrees of freedom is just, remember your sample size is now going to be the number of differences, right? And so it's just going to be the sample size of the differences minus 1. So the number of differences minus 1. Okay? And then how you draw your conclusion is the exact same that we've been doing. Once you have your p-value, right, from step 3, then you can compare it to the alpha level. Is it less than the alpha level? If it is, then you have enough evidence to reject H0. If it's not, then you don't. And then, of course, state your conclusion in terms of the question. Good. So, right, all of this is on your formula sheet, just using diff instead of d's, but hopefully you're okay with that. And then later we'll introduce the confidence interval for the mean of the differences, right? But it looks the exact same as one sample mean, sigma unknown. It's just we're using that same sample information that we just developed, the x bar of the differences, s of the differences, n of the differences. And then down here, the degrees of freedom is the sample size of the differences minus 1. All right. Let me grab this. I think we have an example coming up. Okay, so time for an example. Helps if I'm holding my pen in the right direction. 200 observations were randomly sampled from a survey called High School and Beyond. Classic. The same students. That's a clue. Took a reading and writing test and, a reading and a writing test, and their scores are shown here. I've moved things around. I'm trying to not take up so many pages, but it's hard. Okay, so we've got kind of an observation number 1, 2, 3, or maybe a row number if you want to think of it that way, makes more sense. 1, 2, 3, 4, and 200 observations, right? So this shows you that you have 200 observations, and then we're given the ID number, and this is done for anonymity purposes, right? And so even if the school is analyzing student data, then typically what happens is that one person creates new ID numbers. So you don't actually use the student IDs. You use kind of these secret numbers that don't tell you which student it is, and it makes it impossible to figure out what student this is unless there's some identifying piece of information in the data, but that should be removed, and let's assume that there isn't. So, and then that one person has the key that can join your student IDs and link all that student information later. But when you analyze it, then you give it to someone else, or you might even analyze it yourself. But you should have kind of alternate ID numbers, just so you're not, I don't know, maybe you have some sort of personal bias against someone or for someone, and that would impact the results. So here we've got the reading scores and the writing scores. Let's assume that they're on the same scale. Maybe they're even out of 100. I don't think it actually says, but we'll assume that they're on the same scale, and let's just, for simplicity's sake, say that these scores are out of 100, or percentages. That might make more sense. Percentages. Oh, what an idea. All right. So what I want to do is just let's read through these problems. I'll give you the opportunity to pause it and try these on your own, because you have all the skills already, right? And then we'll, of course, come back and work through the solutions. Sorry, we've got a crazy storm coming in right now. See, does not affect you in the least. So first thing we want to talk about is, are the reading and the writing scores of each student independent of each other? So the reading and the writing scores are not independent of each other. Each of the students, we'll get to that later, we'll consider them to be independent of each other, but the reading and the writing scores are not independent of each other, meaning we have paired data, right? Because it potentially someone with high scores in reading might also have high scores in writing, right? That's not that big of a stretch, right? And then someone with low scores in reading might also have low writing scores, and so we can consider them paired on each individual. And especially because it's the same individual writing the two tests, it's paired. Hey, I did it again, where I just answered it for you. Anyways, I'll try not to do that. Compare the distributions of the two groups. I think I have, let's see here. Oh yeah, I have that down here. So maybe just parking lot that question, and we'll go through it when we do the solutions together. So C, are the assumptions for inference satisfied? That's going to rely on that box plot that I just showed you. So if you want to, you can kind of scroll ahead to there, or just kind of sit on it for a little bit. Here's where I want to get to. Part D and E are the most important. So do these data provide convincing evidence of a difference between the scores on the two exams? That's going to be a full hypothesis test, right? And so really pay attention to your null and alternative hypotheses. And I think I have, you don't have the data. So I think I say what the mean and the standard deviations are. Hey, I should have read through this example before going through it with you guys. Here's the mean and the standard deviation of the differences. Maybe I'll nab those. And how I found the differences was the reading minus the writing score, which should, typically I like to make it match. Yeah, so the reading minus the writing score. Usually I just subtract across. But you might need this little tidbit there for part D. Right. E, suppose we were to construct a 95% confidence interval for the average difference between, so average is the mean, right? The mean difference between the reading and the writing scores. Would you expect this interval to include 0? So I'm not asking you to build a confidence interval yet. We will. But do you expect it to include 0? Now that's going to link back to your hypothesis test, right? Because your null hypothesis is that the mean of the differences is 0, right? And so from the conclusion of your hypothesis test, what do you think is going on in your confidence interval? So I'll give you however long you want to pause it, but I'll give you the opportunity to pause it now. Okay. Welcome back. So I guess I actually need to pause it to bring in the example of the solution. Hang on. Okay. So because this is a large data set, right, I have used R to do these calculations. Now, if we're, if you're using R and then it's nice to have. If not, you can kind of ignore it and just extract the information that you need from it. Right, but I just wanted to show you, kind of get you in the groove of how it would go in real life. So how do you come up with these numbers? Where do they all come from? And so, all right. So 200 data points, we know that, right? That it's way too many to do by hand. So I've used R and like I said, I've kind of shown you. So this data set, the high school and beyond data set, is stored in the Open Intro package. Like I said, this data is paired because we have the same student writing the reading test as well as the writing test, right? And so the reading and the writing scores of each student is not independent of each other, and that's why we have paired data, right? And so that's step one, is figuring out what kind of data do I have here, and then that'll put you on the right path to how do you solve this problem. Or rather, how do you analyze this data? It's not just about solving problems, right? It's being able to analyze data later on in life, or probably more like in work, but that's important too, I guess. So notice that we have numerical variables, and then they can be grouped as either the reading scores or the writing scores. This is more if you actually had to generate this box plot yourself, right? Then you need to kind of think about how does the data need to be stored. For us, we can just kind of ignore this. But I've shown you how I tackled that. So here's the group for the reading scores and the writing scores, and then I've stored them, and then I made a box plot. And so this is a side-by-side box plot, and a box plot that's symmetric, right, or roughly symmetric, means that we also have an approximately normal distribution, right? And so it looks like our reading scores have a little bit wider spread than the writing scores. The writing scores seem to be more compact with a slightly higher median. Remember this line here, the thick line is the median. And so we don't see the mean here, which is what we're going to analyze. But first we have to make sure that we look at this and what do we think is going on here? Right. Generally, I don't see a difference. The overlap in the boxes, which is the central 50% of your data, right? They overlap pretty well exactly. So to me, that's an indication that there's no real difference between the reading and the writing scores. But that's what we're about to find out. So here, what we're looking at is approximate symmetry kind of along the median. And even though this side is a little bit shorter than this side, I'm okay with that. And I'm going to say it's approximately normal. Okay. So we looked at, so the side-by-side box plot, does not indicate any major differences between the distributions of the reading and the writing scores. And that's because of all that overlap. Okay. So unless we're using software, right, then I would expect you to be able to generate this box plot, but otherwise I just expect you to be able to read it, right? So first what we have to do is, okay, so here we've got the reading and the writing scores as two separate samples, but to capture that activity within each student, right, the reading score and the writing score of each student, we need to calculate the differences. And so I've stored the differences as the reading scores minus the writing scores. And then we can make a histogram of the differences, and this looks approximately normal, right? So this here looks approximately normal. It also looks centered on 0, right? So that's important. What does that kind of sort of point us towards? Well, if it's centered on 0, then 0 means there's no difference, right? And so we suspect that there's no difference, right? We see that there is some variation here going from -20 to +20-ish, right? That's a huge spread, but it seems to be centered on 0. So that's just something to keep in mind. Centered on 0. And the spread is roughly -20 to 20. Okay. So because it's approximately normal, we can go ahead and use the t-distribution, which, like I said before, it's always going to be the case. It's just, if you can, check it out, right? If you can generate the histogram is what I mean, then look at it and make sure it's approximately normal. So then I can't remember what part C was asking. Oh yeah, are the assumptions for inference satisfied? All right. So since students are sampled randomly, so I think it even said in the question, oh yeah, we're randomly sampled. Okay, so 200 observations were randomly sampled. So we're told that they were randomly selected. So that's good. So students were sampled randomly, and 200 students is less than 10% of all high school students. So we're not taking up a huge chunk of our population. We can assume that the difference between the reading and the writing scores, so now we're talking about this one sample of differences, right? So that's what we need to check our assumptions around. So we can assume that the differences between the reading and the writing scores of one student in the sample is independent of another. And then here we're talking about this histogram. The distribution of the differences looks approximately normal. So the assumptions for inference are satisfied. And so that's what we looked at here and what we decided already. So then part D is when we do the hypothesis test. And I just want to remind myself what the question was asking. Do these data provide convincing evidence of a difference between the scores on the two exams? So we don't want to know if one is less than the other. We just want to know if there's a difference, which that tells us what to do for our alternative hypothesis, right? So, all right, here we go. First things first, to do the hypothesis like I gave you earlier, we need to know the mean and the standard deviation. So the mean of the differences is -0.545. So this says that X bar of the differences is -0.545. And S of the differences is 8.8866, presumably repeating. I'll just leave it there, but it looks like it might be repeating, but that's okay. Hey, I already said that. The observed average difference, and then the standard deviation. Oh, nice. Okay, so for the calculations, I rounded to 3 decimal places. That's fine. All right. here's our actual answer. So your null hypothesis is always the same. So there's really no work that you need to do to set up your null hypothesis. The only work that you need to do is here to determine if you need a less than, a greater than, or not equal to. And the one-sided test, so less than or greater than, those can be tricky for paired data. But in this case, we just want to know if there's a difference. So finding difference. Right? Because that's what we were asked to do. And just as a side note, that makes this a two-sided test, right? And I like to emphasize it up here, even though we don't need it, we don't need to know if it's a one or two-sided test until step 3 when we find the p-value, right? But this is where we get it from. So now when we do the test, right, notice that technically we have -0 here, but I didn't even write that down, right? But I will erase it. But what are we doing here? We're actually finding, if we kind of talk about this t as we were doing with z's and the t's before, right? We're finding how far is a -0.545 from 0? Is it significantly less than 0, taking into account this spread? Okay. Maybe I'll keep those. Sure, I'll keep them there. No harm. Right. And so here I'll just write down what I just said. Is -0.545 significantly different from 0? Right. That's what we're testing. All right, so once we take into account the spread, notice that I'm using rounded values. So as soon as I use rounded values, my results will change slightly from if I was using software, but they should be pretty close. So we get a t of -0.867. Now, that makes me suspect because it's not beyond 2. Remember, t, we can go a little bit further than 2, but 2 is still a good guideline. So it's within 2 standard errors from 0, which makes me think that I'm not going to be rejecting the null hypothesis, which lines up, right, with what we saw in those box plots. There was a lot of overlap there. And so I already kind of suspected I wasn't going to reject the null hypothesis. Here I am again saying, oh, okay, I probably won't be rejecting the null hypothesis, but we still need to go through and actually do it. So the test statistic confirms our suspicion that there's no significant difference in the reading and the writing scores, but we do have to go ahead and find the p-value. So finding the p-value using the t-table with degrees of freedom, and I'm going to do nd-1, or diff if you prefer. So 200 minus 1 is 199, but if we use the table, so let's go to our tables here. So if I go here and I'm trying to find my 199 degrees of freedom, then I've got 80, 100, and then it skips to 1,000. So 199 is somewhere between 100 and 1,000, but you always have to round down, right? You probably would in this case anyways, but it's just something that you always have to do, right? So, and you should, if you're doing that, you should highlight that you know to do that in your work. So then I say, but using 100 degrees of freedom. Okay. Then we try to place our calculated t, which was this -0.867. Okay. So notice here, so I've got 199 degrees of freedom, but using degrees of freedom equal to 100, we find that our calculated t, which is this guy up here that we calculated, -0.867, but the absolute value of that, so I drop the negative, And once I take that to the table here, it's somewhere between 0.845 and 1.042. And then I can trace it down from those two values that wrap around my calculated t to find my two-sided p-value. All right. Noticing that you have to, oops, you have to list them from right to left. Okay. So our p-value is somewhere between 0.3 and 0.4. Again, that lines up with no significant difference between the reading and the writing scores, right? Because that's a really large p-value. So if you want to visualize the two-sided p-value, right? So here, this was our difference, and we could have used the negative 0.867, that's our t, or here I've used the difference in the scores. It doesn't matter. They behave the same way, right? They have the same shape. The t is just shrunk down. So here, right, we found a negative difference, but for a two-sided p-value, you also pretend that it's happening in the upper end. Okay. Here I've got a little kind of downer point. So technically, but it's nice, it's good to see it and introduce it. But technically the p-value is the probability of obtaining a random sample of 200 students where the average difference between the reading and the writing scores is at least 0.545 in either direction. So it's the probability of seeing something as extreme or more extreme than what you saw in your sample, if in fact the true average difference between the scores is zero, right? Is the null hypothesis. So the p-value is really high, which means that, okay, well, that is likely, right? If I take 200 students, if I randomly select 200 students and I find a difference of 0.545 in either direction or more, then that's the p-value. So our conclusion then, remember, is 3 parts. So I want to highlight those 3 parts. First thing you have to do is you have to compare your p-value to the alpha level. All right. So since our two-sided p-value is between 0.3 and 0.4, it is not less than. If it doesn't tell me what alpha level to use, I'll usually insert something like then the assumed alpha level of 0.05, just because I want to emphasize that, hey, it wasn't given to me, but this is the assumed one. And then what does that mean in terms of the question? Which means, well, if it's not less than the alpha level, we do not have enough evidence to reject H naught. So which means we do not have enough evidence to reject H naught. This means these data do not provide convincing evidence of a difference between the scores on the 2 exams, right? And so we use the mean of the differences to detect a difference on the scores. So you have to really keep track of the words that you're using here. Use purple. Okay. So I think the last part, let me just go back there and check. Suppose we were to construct a 95% confidence interval for the average differences or the mean difference between the reading and the writing scores. Would you expect this interval to include 0? Okay, so let's think about this. If you're not rejecting the null hypothesis, right? So you're failing to reject the null hypothesis. Notice that I'm refusing to use the word except there. Because we can never accept anything, right? We either have enough evidence to reject H naught or we do not have enough evidence to reject H naught, and then we say that we fail to reject H naught. So we did not reject, we failed to reject H naught. So really what we're saying is that we fail to reject this, that the mean of the differences is 0, right? Or at least not significantly different from 0. Now, in terms of our confidence interval, right, that means that 0 should be or is likely in the interval. It actually works out to be, it is going to be in the interval because we use an alpha level of 0.05. So if we were to construct a 95% confidence interval, and I've actually included it here from the R code down below so we can check it. For the average difference between the reading and the writing scores, we would expect this interval to include 0, as our two-sided hypothesis test at the 0.05 level concluded the population mean was not significantly different from 0. So here we can do a paired test in R, and it'll calculate your T. Notice that, of course, R doesn't need to do any rounding, so the T is slightly different, but still very, very similar, right? And we're told the degrees of freedom is the same that we had. And then we have our p-value. It gives us the p-value of 0.3868, which if we think back or look back, 0.3838 is somewhere between 0.3 and 0.4, right? And so we were still able to draw our conclusions from this, but if you want something more precise, then you should use software like this. Our 95% confidence interval that we found goes from a negative number to a positive number, which means 0 is somewhere in that interval, right? Which is exactly what we expected to see. So even if we're not, using software explicitly, you should still be sort of comfortable picking through this information and saying, oh, okay, it just saved me some work of finding the confidence interval. You do, so just as a side note, if you are trying to follow along in R, you do have to have a two-sided test for it to generate a confidence interval, otherwise it won't do it. But that's the default, so it'll just do it. But if you're trying to specify that you want a one-sided test up here, it won't generate the confidence interval, or I think it might only generate half of the confidence interval. I can't remember. But that's kind of a side note, not terribly important for us. Okay, so good. Let's see here. What's next? Confidence intervals. Who knew? I knew. But good. So that's one example. And of course, as you work through more examples of hypothesis testing with paired data, I think you'll find that it's kind of nice, right? It has the simplicity of one sample mean, sigma unknown, but with the predetermined null and alternative hypothesis, it's like potentially the easiest type of question to solve. Once you identify the question type or the data as paired data, then you're off to the races. So we've already seen it on the formula sheet, but let's just bring up the confidence interval for paired data. What's this an interval of? It's trying to capture the population mean of the differences, right? But really beyond that, we don't really need to introduce anything else here. Once you have the formula for the confidence interval and the degrees of freedom, which we already had, we can just kind of go ahead and do a confidence interval at this point, right? And so for each of these, as we work through them, you're going to find that we're just building on the same information. And so I'll need to introduce less and less for you to pick up on, oh, okay, I know how to do this hypothesis test, or, oh, I know how to do this confidence interval. All right. So again, I want to just read this question with you and then give you the opportunity to pause it and try it on your own, because notice there's really nothing crazy going on here, right? So here we go. So an agricultural field trial compares the yield of two varieties of tomatoes for commercial use. The researchers divide in half each of 10 small plots of land in different locations and plant each tomato variety on one half of each plot. So they've got 10 plots, and then they divide them in half, and they put each variety, variety A and variety B, I guess, on each plot. So each plot has a pair of observations. Right? After harvest, they compare the yields in pounds per plant at each location. The 10 differences, so, and here I tell you variety A minus variety B is how I calculated those differences, give the following statistics. X bar, which is actually X bar of the differences, right, is 0.55, and S is the standard deviation of the differences of those 10 differences, right, is 1.23. 123, how original. Is there convincing evidence that variety A has the higher mean yield? Okay, so then we need to think about, okay, if A is higher than B, and this is how we found our differences, what does that mean for us? So it's asking, so it is not asking for a hypothesis test, although we definitely have everything that we need to do a hypothesis test to figure that out. So you have all the information that you need to do that, and maybe that's a good exercise to try. But you'll land on the same information as the confidence interval. So here we have to construct a 99% confidence interval for the mean difference in yield of variety A and variety B to answer the question. Just as a side note, before I kind of let you go and try this, I shouldn't say let you go. We're not there yet. A 99% confidence interval is the same as an alpha level of 0.01 for a two-sided test, right? And so if you're using 0.05, then your results won't really match, right? And so just to kind of keep that in mind. It's a little bit beyond what we have covered so far, but it is something to think about. So a 99% confidence interval is equivalent to an alpha level of 0.01 for a two-sided test. Okay. Okay, so I'll give you a chance to pause it here and try it on your own. Okay. So first thing I want to do is just go through and identify the information here. And so we've got 10 differences, right? So n of the differences is 10. X bar of the differences is 0.55, and S of the differences is 1.23. How original, right? And so now we want to know, is there convincing evidence that variety A has a higher mean yield? Okay, so that sounds like a hypothesis test, right? And like I said, we can go through and do the hypothesis test. We won't, but I'm going to use the confidence interval to answer the hypothesis. Okay? Construct a 99% confidence interval, so that is what we will do using this information. So first thing I need to do is find my degrees of freedom, which is just n of the differences minus 1, which is 10 minus 1, which is 9, which is on the table. So if I go to the table, then I'm not doing this anymore. I have 9 degrees of freedom, and I want to make a 99% confidence interval, and so my T star is 3.250. So I jot that down here. We find T star is 3.250 for a confidence level of 99%. At that point, as long as you lay out your empty formula here, then we can just plug in the values and solve for the interval. Notice that this is, of course, so 1.264 is the margin of error. And we take plus minus from 0.55, which is the mean of the differences. So we get a negative 0.714 if we're rounding to 3 decimal places. It didn't specify, but 3 should be fine. And then up to 1.814. First thing I want you to do is just interpret this interval, because that's what you always have to do when you make a confidence interval. So we're 99% confident that the interval from negative 0.714 to 1.814 captures the mean difference in yield of variety A and variety B. Now, notice that a difference of 0, we're 99% confident that a difference of 0 can happen, right? Because 0, it goes from a negative to a positive. So 0 is somewhere in this interval. So since a difference of 0 is within this interval, we do not have convincing evidence that variety A has a higher mean yield. Now, I want to think about what would this interval look like if variety A did in fact have a higher mean yield? Higher, right? If it has to have a higher mean yield, maybe blue is good. If A had a higher mean yield, our interval, because the difference, so how we calculated the difference was variety A minus variety B. So if A is consistently higher than B, then we would have consistently positive numbers, right? Because, and you can always make up numbers, right? 4 minus 2 is positive, right? And so we would have consistently higher or positive values. So we were on the right track with a positive 0.55. So that made us suspect that A maybe had a higher mean yield, but we had to do the test to figure it out. And it turns out not significantly higher. It's higher, but not significantly higher. Right, and so if A had a higher mean yield, our interval would have been consistently above 0, right? Would have been consistently above 0, right? So for example, if this 0.714 was not negative, if it was positive, right? So from positive 0.714 up to positive 1.814, then we're 99% confident that that difference is always going to be positive, meaning variety A would have a higher mean yield than variety B, right? So that's just how we can use a confidence interval to test a hypothesis, right? So pretty cool. A benefit with the confidence interval is it gives us some value to, well, so sure, if there's a difference, great, good to know. But then here from the confidence interval, we find out what that difference would be. Right, so pretty cool. All right, so that's paired data. Now I want to talk about two independent sample means. So now you've got two samples. They have nothing to do with each other, but they're measuring the same thing, and you want to compare those means, the mean of group A to the mean of group B. And this is arguably one of the most common tests that you do in real life. So it's really important, but we had to kind of build up to here and introduce all the little brothers along the way, kind of thing. Okay, so let me organize these notes here. Okay, so like I was saying, the two independent sample means is what we've been building up towards, and it's the one that you're probably going to use in real life. It's kind of weird now that we are about to introduce kind of how do we compare two sample means. It's kind of weird to think about back to the one sample mean, where, okay, so you have one sample, you want to compare it to a number. That's going to be pretty rare. It's going to be, how does the mean of this group compare to the mean of this other group? And where those two groups are independent of each other. So when we've collected two samples of numerical data that's independent, we're going to analyze the difference in the means. Notice, and I've emphasized it later down here, but notice here I'm talking about the difference in the means, whereas in the previous section with paired data, we talked about the mean difference. Okay, so right down here, I've got, we need to be very careful with the wording, right? And so gets a little finicky there, right? So, but let's go back, kind of introducing the problem here. So if we're interested in comparing the averages of two samples that are independent, of course, we use the two sample t-test. Okay? And the problem then becomes, okay, well, we can't use that trick where we subtract one sample from the other, right? One observation from the other, like we did with paired data, because we don't have that relationship anymore. We don't know which one to subtract from the other, so we can't do that. Which means that, okay, so then we're stuck with these two columns of data in your spreadsheet, right? Which means that you're going to have a sample size for each of those columns. You're going to have a mean for each of those columns, and you're going to have a standard deviation for each of those columns. And so now we basically double all the information that we need / have. Okay, so there's going to be two columns of data to deal with in your data set. Okay, so from each column, you'll be able to calculate a mean and a standard deviation, and of course, get the sample size. And here, a cool thing about this test, and I just need to see if I can do it. Can I do it? Emoji? This is very important. I need the cool dude emoji. And oh, that's not what I wanted to do. Hey, I want the cool dude emoji. Okay. Whoa, what's going on here? ABC. Okay, I think I did it. And it was all worth it. A cool thing about this test is, and I didn't even pause the recording to do it, oh well, is that the columns don't even need to be the same length, which I kind of spoiled for you already, but which means that we will be able to deal with different sample sizes in the two groups. So usually we kind of, I don't know, for some reason we want to have the same sample size in both of the groups, just kind of human nature, I guess. You know, if you sample 20 people from first year, then you probably want to sample 20 people from third year or whatever, if you're talking about a university, that kind of thing, but you don't need to. Okay, that's just a weird thing that we kind of feel intuitively, I think, but we don't actually need it. And I think that's really cool. So I do. All right. So we need to be really careful with the wording, and I'm going to draw a little box around this because it can get very confusing, right? So for matched pairs or for paired data, we're analyzing the mean difference, right? The average difference, the average of the differences. For two sample means, we're analyzing the difference in the means, right? Mean A minus mean B, right? I hate to use the word difference, but there's a huge difference, right, between these two differences, right? The mean difference versus the difference in the means, okay? Notice that on the formula sheet, you might not have noticed it for the matched pairs, but I've actually emphasized that here. This is for analyzing the difference of two means, right? The difference in the means. And then for paired data, right, we're analyzing the mean difference. So it's on here, it's subtle, but it's on there on the formula sheet. Okay. At this point, right, we've seen, I want to say, 3 different types of hypothesis testing and confidence intervals. So at this point, you should be more comfortable with me just giving you this chunk of the formula sheet. So the 2 sample means chunk of the formula sheet. And even though we haven't done this problem, right, you should feel kind of comfortable saying, oh, okay, so that's what my null and alternative hypotheses are. All right, sold. How does the mean of group 1 compare to the mean of group 2, right? Maybe they're different. Maybe they're not significantly different, right? And then, okay, so this T calculation looks nasty, and it is kind of a bore. But what's nice is as soon as you see a T, right, once you've calculated this T, even though getting to that T is a little bit harder than what we've done, right, math-wise, once you have a T, it behaves the same way. You use the T table, you need degrees of freedom. What are the degrees of freedom, you ask? Well, it looks weird, but once you boil it down, it's going to be okay. It's the minimum of n1 minus 1 or n2 minus 1. So the minimum of the sample size of group 1 minus 1 or the sample size of group 2 minus 1. What does that translate to? It just translates to the smallest sample size minus 1. Right? So here, this is really just saying take the smallest sample size minus 1. Oh, maybe I should write it out. Right? So that's how you're going to find your degrees of freedom. This is just math notation, but once you kind of go through it slowly, then you'll see, okay, it is shorter than writing smallest sample size minus 1 every time. There is actually a more complicated degrees of freedom formula, which software uses. So if you're ever running software and it gives you a different degrees of freedom, it's able to compute that difficult degrees of freedom very easily. We're just using this for simplicity's sake, and it gives us good enough results. Okay. Okay, and then the confidence interval is for the difference of the two means, right? So here, mu1 minus mu2, well, the best guess for mu1 minus mu2 is x1 bar minus x2 bar, right? So same layout as before, and notice that this big square root is the same square root that we had here, right? So once you've calculated it once, if you have to do a hypothesis test and a confidence interval, you can just reuse that number, right? Okay. Let's see here. So the next thing I wanted to say is actually here on, gonna need to adjust my pages here. Just a second. So we already established that we're gonna have sample information from each sample, right? Sample 1 and sample 2. Usually I end up calling them group 1 and group 2 because otherwise it's too much sample mean, sample standard deviation, sample 1. Ugh, it just gets confusing. So group 1, we're gonna have, so denote it with a subscript. And this is just to show that, okay, all this information with a subscript 1 is from group 1, and then of course subscript 2 is from group 2. We want to set up our null and alternative hypotheses in terms of how the two population means compare, right? So before we were talking about how does the mean compare to some hypothesized value mu naught. Now, it eliminates the need to find that number because we're really just comparing how does mu1 compare to mu2. So we should use question-specific subscripts to differentiate between group 1 and group 2. Or if you define group 1 and group 2 early on, then you're allowed to use 1 and 2. But for your null and alternative hypotheses, because it's going to be really important, if we are comparing, let's say, so here for full marks on a test, I know, cracking down, you must use question-specific subscripts. Okay, so what I mean by that, right, if we're comparing, I want to say like apples and oranges, but O looks like a 0, so I'm trying to avoid that. If I'm comparing bananas and tomatoes, I have no idea why I would want to do that, right? But then my null hypothesis should be mu b equals mu t, right? Usually the subscripts kind of are obvious from the questions, right? How does the mean of the bananas compare to the mean of the tomatoes? That's a weird example, but that's what I mean by question-specific subscripts. And I'll clarify here in H naught and HA. Okay. Because you'll notice that I'm even I'm sloppy. Even I cut corners when I do the T. I'll usually just do X1 and X2, but I will define which group I'm calling group 1 and which group I'm calling group 2. So then you're allowed to do it. But I want to see question-specific subscripts in your null and alternative hypothesis. So I like to set them up this way, right? However, you could also set it up like this, right? Because you are talking about the mean or the difference in the means. So then, just like for paired data, you could say that your null hypothesis is that mu1 minus mu2 is 0. There is no difference or no significant difference in the means, right? So here it kind of, it's nice because it links back to the difference in the means. But for me, I don't know, I just find this more compact. It's easier to figure out the sign, right? Here, if you're using the actual differences, you'd have to figure out, okay, if it's less than 0 or greater than 0. Whereas here, you're just comparing the two groups. Notice what I've done here is I've just subtracted mu2 from both sides, right? And that's how you get mu1 minus mu2 on the right-hand side, and on the left-hand, on the left-hand side and on the right-hand side, yikes. You would have mu2 minus mu2, which is 0, right? So that's all that's happened here, is I've just subtracted those mu2s over. But I find that this is a little bit trickier. You're definitely allowed to use this if it makes sense to you. If it makes more sense to you, go for it. But I'm going to use the first option in the solutions just because I find that it's a little bit easier to deal with. But it's nice to have seen this because we always do our test assuming that the null hypothesis is true. So then when I look at my formula, which is this, and I just want to scroll back to the formula sheet because again, I think I might just have omitted it, because what does this become? This becomes 0, right? And I just want to go to the formula sheet, and it might be easier to go here. Yeah, so I don't even have the minus 0 on here, right? Or minus mu1 minus mu2. So that's fine because it's always going to be 0 again, right? And so, oh, I guess I guess I should read ahead. Or maybe I did and it was kind of subconsciously triggered. Anyways, so this is technically what's going on. How far is the difference in the means from the sample from the hypothesized difference in the means, right? Which is going to be 0. So how far is this difference from 0? And then once we take into account the spread, which looks a little bit different, just because we have 2 sample standard deviations and 2 sample sizes. One thing I want to point out here is that, okay, well, notice that only the standard deviation is squared, right? So you want to make sure that you square those and then divide by n, and then do the other one and then add them up and then take the square root. Usually if I get frantic texts from people saying, oh, I'm not getting the same results, it's because they've forgotten to take the square root, because a lot of work went into this, right? You feel like you're done, but you're not. Okay, so so we always do our test assuming the null hypothesis is true, which means that mu1 minus mu2 equals 0, which we could also get from mu1 equals mu2, right? If mu1 equals mu2, then this would also become 0. They're the same, right? So, all right. Once you've calculated your t, right? So a t-score that tells you how far x1 bar minus x2 bar is from 0, then you can use the t-table just as we have been doing. I mentioned the big nasty degrees of freedom, right? So technically, if you're using software, this is what the computer will use as the degrees of freedom. We're not going to do that. We're satisfied using a more conservative approach for our hand calculations, which is just the degrees of freedom minus of the smallest sample size minus 1. Right, notice that this is simply taking the smaller of n1 minus 1 and n2 minus 1 as the degrees of freedom. And then your conclusion, once you have your p-value, right, which is what requires your degrees of freedom, but besides that, we know what we're doing now. Right, how you draw your conclusion stays the same for all of these, and that's always the case. Okay. So no wonder I made you memorize that, how if the p-value is less than the alpha level, then you have enough evidence to reject H0, right? No wonder. Good. Notice that, whoops, I zoomed out too much. Notice that all of this information here that we just went through, that's really just a long version of everything that we were able to establish from the formula sheet, right? So that's what I mean by, okay, at this point, I can probably just give you the formula sheet and you'll be able to piece things together, right? And so, but of course, we're going to go through and do it, but that's where you want to be headed, right? Okay. Let's do an example. Weights of diamonds are measured in carats. The difference between the size of a 0.99 carat diamond and a 1 carat diamond is undetectable to the naked human eye. I wonder, why does it have to specify naked? I don't know. But that's okay. But I've never noticed that before, but today I did. But does the price of a 1 carat diamond tend to be higher than the price of a 0.99 carat diamond? I guess this should say carat diamond. we're going to test to see if there's a difference between the average prices of 0.99 and 1 carat diamonds. Specifically, if 1 carat diamonds are more expensive than 0.99 carat diamonds. In order to be able to, so here's where it gets a little bit dicey, and sometimes we have to do stuff like this, so it's good to introduce it and have seen it. So in order to be able to compare equivalent units, right, that's important. If the mean is measured in different units, then we can't do those comparisons, right? And so to convert to equivalent units, we divide the prices of 0.99 carat diamonds by 99 and 1 carat diamonds by 100, and then we compare those average point prices, right? So 1 carat has 100 points and 0.99 carats has 99 points. Let's say you collect 2 random samples of diamonds, 1 sample of 1 carat diamonds and 1 sample of 0.99 carat diamonds, and you find the following summary statistics of the point prices. So the 1 carat diamonds, this is in dollars per point, have a sample mean of $53.43 per point, right? Which for a 1 carat diamond, we would have to multiply by 100 because a 1 carat has 100 points, right? So that would be the overall price. With a standard deviation of 12.22, and our sample size was 31 carat diamonds. 0.99 carat diamonds, same information is given, and it's very typical that we set it up in a table like this because it's kind of the clearest way to communicate this information. It could have been baked into the text here, but I wanted you to see the table because now you have 2 X bars, 2 S's, and 2 N's, right? So 2 different sample sizes. Notice that we had a slightly smaller sample of 0.99 carat diamonds. That's totally fine. We can handle that. So here we go. Is there evidence that the average point price of 1 carat diamonds is higher, and I'll emphasize that, is higher than the average point price of 0.99 carat diamonds? So what I want you to do is just pause it here, work through, I guess I should tell you what to do first. Work through it, try as best you can, and then meet me back here for the solutions. Okay, so the calculation is a lot of work, right? But you just got to take it slow and be careful, and it'll all just kind of fall into place. So first thing we need to do is, because remember, especially on the final exam, right, you're going to be reading all these different types of questions and you have to figure out what type of question is this. Here it's easy because of course we're in the two independent samples section, so of course it's 2 independent samples, but start to pick up on what makes it 2 independent samples. And that's going to make it easier when you're reading a bunch of problems and trying to figure out what type of question it is. Because then once you've decided what type of question you have, that'll put you in, on a specific section on your formula sheet, and you just do those calculations, do that work, and then you're safe. 1 carat diamonds and 0.99 carat diamonds, there's no reason why we would think of them as paired, right? And that's okay. They're just 2 independent samples. And especially because I have the means and the standard deviations and different sample sizes, all that is pointing towards 2 independent samples. So these are 2 independent samples, as there's no way to naturally match one observation to another. And here I'm gonna, just in case I slip up and only use 1 and 2, I'm gonna define group 1 as my 1 carat diamonds and group 2 as my 0.99 carat diamonds. You could switch these up, but I like to have them in the order that they appeared to me. And so my 1 carat is my group 1 and 0.99 carat is my group 2. Okay. So, in terms of my hypotheses, now remember for the hypotheses for 2 independent samples, I do want to see question specific subscripts, even if it's something like mu1 equals mu of 0.99, right? That's fine. That is what it is. And then what we're hypothesizing and what we want to test is if mu1 is greater than the mu of 0.99, right? 1 carat diamonds, do they have a higher per point price than 0.99 carat diamonds? This is a one-sided test. Why? Because we only care about one side, one extreme, right? Okay. Step 2, do the test. Right, do the calculation, and that's where we get into a lot of work, right? And notice here, I was even lazy, and I used 1 and 2. Probably a copy paste error, and I forgot to adjust it, but that's okay because I defined my group 1 and group 2. I'm okay. So I plug in all the values, paying attention to squaring these values before I go ahead and divide, right? So notice that they've been squared, and then don't forget to take the square root here, right? Those are the most common mistakes that I see for these calculations. And so just really kind of slow down and work methodically, right? But what do you have to do? I've shown it by writing out each step of the calculation, right? And so first you're going to deal with the squaring. Well, I guess I subtracted the numerator. You can work the numerator and denominator side by side. That's allowed. So I simplified the numerator, and then now I'm going to focus my attention on the denominator. So in the square root, I want to work these squared standard deviations on each side here. Then I'm going to divide by the sample size. So notice that now I have these as numbers, which I can then add up to get 12.69. And then when I take the square root, I get 3.56. Okay, so my t ends up being positive 2.507 rounded to 3 decimal places, right? We use 3 decimal places because our t table that we're using has 3 decimal places. So you want to keep at least 3. The test statistic makes us suspect that there might be a difference in the mean point prices, right? It's more than 2. And so right away, I'm starting to think that, oh, okay, maybe there is a significant difference here. Okay, but let's find the p-value, and then it's all going to hinge on that. So the p-value, first we have to find our degrees of freedom, and we're just using the simplified one, right? Which is the minimum of n1 minus 1 and n2 minus 1. Notice that I'm doing the calculation inside here, and I want you to do the same, right, when you're doing your work. So the minimum of 30 minus 1 or 23 minus 1, we know it's going to be 22, but I want you to show it, right? And so the minimum of 29 or 22 is 22, right? And so that's how we get to the degrees of freedom. But then once we have it, we set it up the exact same way as we did before. We take our calculated t and figure out where it would be placed on the 22 degrees of freedom line. Notice that with our rounding, we're dangerously close to 2.508, but notice 2.50664449999 is still less than 2.508, but you do have to be careful, right? So that's something to keep an eye out for. So then if we trace down, notice that we want a one-sided p-value because we want to know if the 1 carat diamonds are more expensive, right? Have a higher point price than the 0.99 carat diamonds. And so I'm not going to go to the table here because we've done that enough now. but hopefully these are the values you land on. And then your one-sided p-value is somewhere between 0.01 and 0.02. Okay. We have a one-sided test. So here I'm just emphasizing that since the alternative hypothesis mu1 is greater than mu 0.99, so we only care about one extreme. That's what I said here, but it's good to have it. So since our one-sided p-value, so our conclusion, right? Let's break it down. It's going to have three parts again. All right, so here we go. First thing we want to do is compare our p-value to the alpha level, right? So since our one-sided p-value is between 0.01 and 0.02, it is less than our assumed alpha level of 0.05. We weren't given an alpha level, so I'm assuming it's 0.05. Which means we have enough evidence to reject H naught in favor of HA. Okay. That's kind of part two here of our conclusion. And then what does that mean in terms of the question? Well, in terms of the question, if we're rejecting H naught, that they don't have a significantly different point price, mean point price, in favor of mu1 is larger than mu of 0.99, well, this means that there is evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds. Okay. So you always have to state your conclusion in terms of the question, but usually that just means rewording the question as an answer. Right? Nice. Good. Arguably, the most work is calculating that t, and then once you have the t, you just use it like we have been. Okay. Same thing with the confidence intervals. Once you have the formula for the confidence interval, then we can build the confidence interval and interpret the confidence interval, reminding ourselves that we are analyzing the difference in the means, right? So our interpretation has to be about the difference in the means, mu1 minus mu2. I also want to point out, in case it wasn't clear earlier, this is the standard error of x1 bar minus x2 bar. Right, so this part is always going to be the standard error of whatever we're building around. Right? And then our T star, we find it the exact same way that we did before. And again, our degrees of freedom, we already saw how to find that, so that's not bad either. Okay, let's see here. So we've got another example. And as we're reading this problem, I want you to think about what makes it two independent samples, right? So it's kind of a long one, but that's okay. When the time comes, I like it because it's like the stuff of comedy shows. So here we go. So when the time comes for a group of people eating together at a restaurant to pay their bill, sometimes they might agree to split the costs equally, and other times they will pay individually, right? And it's always kind of like, I don't know, every comedy I've ever watched, it comes up at some point. So kind of funny. If this decision was made in advance, would it affect what they order? So some researchers conducted an experiment where 48 Israeli college students were randomly assigned to eating groups of 6, 3 females and 3 males. Before ordering, half the groups were told they would be responsible for paying for their meals individually, and the other half were told to split the costs evenly among the 6 participants. Right? So you've been randomly assigned to some group, and you're told, okay, you guys, you're all just paying for your own meals, order based off of that, and then the other groups, okay, you guys, you're just going to split it, go have your meals. Okay, so the 24 people paying individually had a mean cost of 37.29 Israeli shekels with a standard deviation of 12.54, while the 24 people splitting the bill had a higher mean cost of 50.92 Israeli shekels with a standard deviation of 14.33. And then just some background information. Both distributions are reasonably bell-shaped. Okay, that's good, because then we can go ahead and just follow assume it follows the normal distribution, or at least use the t-distribution. And so that's good. So that's for checking assumptions, which we're not really focusing on here. But so then we're going to construct a 95% confidence interval for the difference in the mean costs between the two situations. Okay. So I'll give you some time to pause it here and work through it and see how you do. Okay. So I'm going to start by just defining my groups. So I'm going to let the group 1 be the group paying individually, and I'm going to extract the information that we're given here. So let's see here. So the 24 people paying individually. So my N1 is 24. Had a mean cost of 37.29. So my X1 bar is 37.29 with a standard deviation of 12.54. So my S1 is 12.54. And then I let group 2 be the group that's splitting the bill. So the 24 people splitting the bill, oh, maybe I should use a different, or a color that's clearly different. So N2 is also 24. That's fine. They can be the same sample size. They just don't have to be. Had a higher mean cost of 50.92. So X2 bar is 50.92 with a standard deviation of 14.33. Let me see if I can. S2 is 14.33. So in terms of our calculation, right, first thing we need to do is find our degrees of freedom, right? Our degrees of freedom is going to be our smallest sample size minus 1, but they're the same sample size, so it's going to be 23. How do we show that? I want you to show it using the minimum formula. Here, hang on. Let's see here. Trying to bring it in here. So using the t-table with the degrees of freedom, so this I'm just grabbing from the formula sheet, and then I'm plugging in my sample sizes. This is all just like going through the motions, right? It's not hard, it's just how we should show it properly. And so with 23 degrees of freedom, for a 95% confidence interval, we get a t-star of 2.069. So we have our t-star, we have our x1 bar, we have our x2 bar, S1, N1, S2, N2. So we have all the information now that we need to construct this interval. So let's go ahead and just grab it. Oh, I guess I need another page here. Rats. Okay, so once you plug in your values, right? Again, it's kind of tedious, but just go slow and make sure that you end up, once you're finished with the square root, you should have 3.86 or 3.8869466638. Okay, so then we find this interval, and money goes to 2 decimal places, so I'm going to round to 2 decimal places. Notice how both of these are negative, right? So they're consistently below 0, right? That's something to kind of keep an eye out for. So now it's time to interpret this interval. So we're 95% confident that the interval from negative 2167 Israeli shekels to negative 5.59 Israeli shekels captures the difference in mean cost between these two situations, right? So it's the difference in the mean costs. And so that's our interpretation. And then I've added on, as this interval is consistently below zero, right? So both of those, the whole interval is negative, right? So below zero, consistently below zero. And we analyze the individual minus the splitting. So paying individually minus sharing the bill. We can say that splitting the bill consistently yields a higher average cost because that's what we were subtracting from paying individually. So it's consistently higher than paying individually, right? So we can gather a lot of information from the confidence interval. And on that note, we finished chapter 5, but I do want to go on a little bit of a rant about p-values. So we're using p-values because it's kind of the norm, but the industry is sort of moving towards just using confidence intervals for this reason, right? We're able to draw conclusions, but we're also able to see the values that we're dealing with, right? How big of a difference are we expecting to see here? And so one caution that I kind of want to leave you with is if you have a p-value that's on the verge of 0.05, for example, then you want to think about the consequences of rejecting H naught if it's really close. So if it's a close call, then you kind of have to think about, okay, well, is this going to cost me a lot of money? Because there isn't that much evidence to do it. But more on that on another day. But here, right, we can use this confidence interval and we can use it to draw conclusions in terms of hypothesis test style question. Anyways, nice work. That's where we're going to end for numerical data. So analyzing numerical data, or I should say inference for numerical data. And then in chapter 6, we're going to do inference for categorical data. So get excited.